Okay, by my clock, it is 9 o'clock Pacific time. Good morning, everyone. Certainly want to welcome back all of you who were able to join us on Tuesday for our opening module on this entanglement science workshop. Certainly want to welcome new folks, any of you who were not able to join us on Tuesday. I think you unfortunately missed a pretty good opening session, but certainly glad to have you here today for what I think promises to be another, excellent session. For those of you who weren't with us, my name is Dan Lawson. I'm with the NIMS West Coast Region Protected Resources Division, and I'll be the General Master of Ceremonies and a common face you'll see throughout the rest of the workshop. I think I first want to start off with a little bit of a recap from the Tuesday session. In that first module, we covered some of the big picture management perspectives that folks have and their need for science coming, as they were coming into the workshop. I will note that I think I heard from each state, and I can certainly vouch from the NIMS West Coast region perspective and all of our various science and management roles. But I think each state, made a fairly clear statement about, needing more information about, whales and other marine species, particularly regarding, how to monitor their spatial distributions in a cost-effective manner. They wanted that, information that would allow them to detect changes in, those distributions and over time, and particularly as, that information would interact with the aims and purposes of their management measures, that they're designing to, try and avoid entanglements. And that was really foremost on really all three states' minds. Again, is also on our mind here in the NIMS West Coast region coming into the workshop. We also started exploring the state of some of that science surrounding different aspects of monitoring marine species and how that can be useful for management of the entanglement issue. I think we had a really good discussion about needing tools that will help understand and predict, the co-occurrence of whales and West Coast fixed fishing gear, at the finest scales that we can possibly get, and that we also needed tools and information that would help us predict how behavior might influence entanglement risks in different places and different times. We covered a number of other things as well, and I know we left a lot on the table really on Tuesday that we weren't able to really get into. I know one thing in particular that I had been wanting to explore a little further was, the use of some of the observational and survey data, efforts that are ongoing, efforts that are underway to further develop those tools. But I think one thing that we did here, there was a really strong interest in predictive models for marine species distribution, and certainly from the management perspective. And to me, that really does dovetail nicely into what we're going to talk about today, which is really looking at the state of science and ecosystem monitoring, particularly from a modeling and a data synthesis perspective. And I'm hoping that we'll end up through at least part of today's discussions connecting that back to what we talked about on Tuesday. So following this first session this morning, we'll then turn our attention to a different side of the co-occurrence equation, which is really the science of understanding the dynamics of a fishing effort in West Coast fixed gear fisheries. I think before I turn it over for a quick tech briefing, particularly for those of you who may be new today, a couple of reminders here. First, remember that you can go to the workshop website for all the event materials, including webinar links and materials for each session, the agenda, and relevant presentation abstracts. Following the first session and some input that we had, we are certainly looking at what we can do to make additional materials available. In particular, we're hoping that we're going to find a way to make copies of the PowerPoint presentations available on the website, following conclusion of the workshop. We will be developing a summary report of the workshop, including, discussion highlights. Not sure on the timetable. I think we're aiming for this fall, to be able to get that summary report completed and up on the workshop webpage, hosted by the Ocean Protection Council. I do want to remind folks that we are recording the workshop, primarily for the purposes of informing the summary report and being able to go back and make sure we capture the discussions accurately. We may make the recording of the presentations available, if that's something we can work out. But at this time, we're not planning on making the panel discussion, the audio of that available. We'll rely generally upon that summary report to highlight the main points of the discussion. All right, with that, I will turn it over to Dana for a brief orientation to the WebEx platform for those who need it. Dana.
Thank you, Dan. And this is Dana Stefan from RAS Strategic. And I also have my colleague, Kristen Durance, on the line, and we will be offering the technical support during the workshop today. We wanted to just give everyone a quick orientation to the WebEx features and to let everyone know how to engage today during the workshop. So if you look at the bottom of your screen, and on the right corner of your screen, you'll see the icon with participants. So that's the participants panel, and you can see the list of panelists once you click on that. Probably the most important feature for you today will be the Q&A box. So again, at the bottom of your screen on the right corner, if you click on the ellipsis icon, you can open the Q&A box, and we encourage everyone to submit questions and comments through that Q&A box. Please note that given the number of people that we have on the call today, we may not be able to address all your questions, but we will definitely consider all your input. So please make sure to use respectful language and make sure that your questions are phrased clearly. If you have any audio issues, again, if you click on the ellipsis icon, which is on the left side of your screen, you can open the audio connection. And if, for example, if you join through your computer and you cannot hear us, you can switch to your phone. And again, if you have any technical issues, you can also email my colleague Kristen at kdurance@truststrategic.com. Her email is actually currently on the slide right now. And with that, I will turn it over to Dan.
Okay. So as I mentioned, we're going to have two sessions today. The first one is really sort of an extension of what the conversation that we started on Tuesday, which is regarding the forecasting and monitoring of marine species dynamics. And the focus of our session today is going to be on the modeling part. When I think about what we're going to hear today, I primarily see them as, we're going to see presentations that relate to scientific tools. And these are tools that, could be used, as predictive models of, whale migrations and distribution. And we'll also hear about tools that, really give us insight into the state of key ecosystem features. Another term I think you'll hear is indicator, of things like, available prey habitat. And how the dynamics of that can help us understand, what whales may have been doing in the past as we're trying to understand this issue, and what we should expect that they are doing, currently or will be doing in real time, or potentially even looking ahead to tomorrow. I think all of these tools and products that you're going to hear about today, as far as I understand them, I mean, they're not a product of just a small number of observations or a small data set, but these are tools that represent a culmination, of many years of observations, data collection, really well thought out synthesis, and validation of these models. So in short, I think you're going to hear and see what I would consider state-of-the-art science here that does summarize a great deal of the understanding of the dynamics of marine species off the West Coast. And I think the challenge is for us laymen like me is, okay, with these tools, we got to figure out what we're going to do with it. The general format today, we're going to have a series of 4 presentations. They're going to be on the order of about 10 minutes long from each of our presenters. Following the presentations, unlike today where we took a break, we'll move directly into a panel discussion. We'll call a number of additional folks up as we did on Tuesday to join for that moderated panel discussion. We'll aim to pause for clarifying questions in between speakers, as we go along, if time allows. Certainly we did very well on Tuesday in terms of, presentations, running on time, and we were able to make a little space for some clarifying questions before we got into the panel. So we'll see how it goes today. We invite all participants in the webinar, to use the Q&A function of WebEx and submit those questions and comments, throughout the presentations, similarly throughout the panel discussions. As we did on Tuesday, the collective team here will work to see what we can do to address the questions, within the discussion or virtually in response, as a group here. So for this first session, the 4 presentations that we're going to have are from Jaime Yankee of Point Blue Conservation Science. Next, we'll hear from Karen Forney from the Southwest Fisheries Science Center. Then we're going to hear from Brianna Abrams from NOAA Fisheries, although starting even during the course of this workshop, I believe we'll be starting an association with the University of Washington. Congratulations, Brianna. And then finally, Jared Santora from the Southwest Fisheries Science Center. For our presenters, a couple of reminders. Obviously, we're really aiming to stay on time. We're going to provide you cues so that when you're nearing the time limit. With 2 minutes left in your time, there'll be chimes. And then when you reach the 10-minute mark, there should be a bike bell indicating when time's up. And certainly I'll be there with you to help bring the presentations to a close there. I think, again, for presenters, I think the general programs. Some of you will be controlling your own slides. Others of you, please remember to advise, the Ross Strategic Group to advance your next slide when you need to do so. Okay, I think that is about all I've got. So I think let's go ahead and start the presentations. Jaime Yankee, please start.
Hello, thank you, Dan. Hello, everybody. Thank you for the invitation to be here today. I will talk to you about changes in the abundance and timing of migration of whales in Central California. I would like to thank my co-authors, Caitlin Ingman, Ellen Hines, and Piero Mazzini from the Estuary and Ocean Science Center, and Davin Cotton from Point Blue Conservation Science. I should mention that this work was Caitlin's research for her master's, but she cannot be here today. Next, please. You probably have seen versions of this slide already from others. This slide shows the number of confirmed whale entanglements from the NOAA NIMS records. From 1983 to 2017, the main point here is that the number of confirmed entanglements used to be about less than 10 until 2013, and then they spiked to really high numbers from 2014 onwards, with really record numbers in 2016. The other thing to highlight here is the blue whales were never on the record. They were never reported except for 2015, 16, and 17. Next, please. The purpose of our work was to show you some changes in sightings and timing of migration of humpback and blue whales around the Farallon Islands. In the map, you can see the location of the Farallones, and we can see about 25, 30 miles around the islands on a good visibility day. The Farallon Islands are located 30 miles from San Francisco, And we have been tracking whales there since 1987 as the whales are migrating into the area during summer and leaving the area late in the fall. And the overall idea here is that we hypothesize that changes in the timing of migration of whales in Central California were driven by environmental conditions. Next, please. This is, I guess, we observe whales from the lighthouse hill on the islands. That's kind of a view on a day with not amazing visibility. Since 2013, we have been using the Whale Alert app, and that data that we collect on the islands becomes available online within 2 hours of our observations. And you are all invited to go and see our data on the web. Next, please. The methods, we use data from 1983 to 2017, about 24 hours of daily whale counts collected on the island. We use negative binomial regression to evaluate trends over time, and then we use linear models to look into trends in the timing of migration and to identify potential drivers. Things that we look at, the drivers, were temperature, sea surface temperature, sea surface salinity, an index of fronts around the island, a boiling index, the timing of the spring transition, and then climate indices such as the Southern Oscillation Index, the Pacific Decadal Oscillation, and the North Pacific Gyre Oscillation. Next, please. This figure shows the interannual trends in the whale count when we summarize the data per week from 1993 to 2016. You can see humpback whales on the left and blue whales on the right. What I'm trying to show here is that with the humpbacks, and this matches some of the charts that were shown by John Kalmakidis yesterday, for the humpback whales, there was little change from the beginning of the series until about the mid-2000, and then there is a rapid increase in the number of whales observed from the island. In the case of the blue whales, there is no clear trend. There's high variability, there's ups and downs, there's lower values in the 2008, 2010, and then it appears to increase again. But again, there's truly no trend there. Next, please. This figure shows a summary of our observations from humpback whales. And what we showed that from 1993 to 2017. At the bottom, we have January 1st of every year. To the top, we have December 31st. And each one of these box plots represent when we see the whales and we track them through their the observations until they leave. And the box represents when we hit that 10% of the animals were observed by the island, the middle point when we got to the median, and the top of the box when we had that 90th percentile. The red line is when the fishing season closes for the Tangerine crabs, and the green line is when it opens in November 15th. The main point here is that for most of this series, whales used to be present in the vicinity of the Farallon Islands when the fishery was closed. But since 2012, and particularly in 2014, 15, and so on, we saw a lot of these whales arriving really early into the spring. So we thought it's like, we wanted to look whether there was a trend, whether this trend is real or not. Next, please. This figure shows internal trends in the timing of migration, also just looking to, we have humpbacks to the left, blue whales to the right. And the main point here is that we see for both humpbacks and blue whales, significant changes in the timing of arrival, with humpbacks arriving about 120 days earlier now than they did back in 1993, and blue whales arriving now about 100 days earlier than they did in 1993. And I'm not showing gray whales, but we found a similar pattern there as well. The departure has changed very little. It's not significant for blue whales and barely significant in the case of humpbacks. Next, please. So if we look into the drivers for humpback whale early arrival, we see that the most dominant predictor was sea surface temperature, and all climate indices appear to contribute to the model. And if I summarize this in, I guess, simple words, the idea was that early arrival for the whales occurred during warm, not productive years, as indicated by the winter PDO and MTGO values, and just to follow a productive year, as indicated by the La Niña conditions in the previous year. The models were significant, and they fit relatively well the data used here. So what we did next was to try to say, like, so who cares about this? Why is this important? Next, please. And we played with the data on whale entanglements from California with the idea to see is like, what contributes to the rate of entanglements that we see for California as a state. And we found that monthly entanglements increase as counts of humpback whales were increasing. And then monthly entanglements had increased in years when we had earlier arrival. The ecological effect of this, of counts and arrival, are strong to the model. The models are significant, but the overall fit to the data is low. So we cannot forecast to you if there's going to be entanglements in the following year just based on whether they're going to arrive early or not. But there's some sort of an indicator there that we expect to see greater entanglements if the forecast for next year is that we'll have an El Niño or an anomalous ocean conditions. Next, please. So in summary, whale sightings have increased over the study period. Arrival time is earlier for humpback and blues. Timing was influenced by warmer waters and non-productive ocean conditions. Early arrival leads to longer periods of time when whales are exposed to fishing gear, elevating the risk of entanglements, and actions to decrease the overlap between whales and fisheries in the spring should be encouraged. And that's all I have to say. Next, please. Thank you, Vlad. Yeah, thank you for the invitation to be here today, and I'm happy to address any questions.
Yeah, thank you, Jaime. I think I have a really sort of natural question falls out of this. So, your work, focused in the Farallon Islands. How do you think the analysis that you've done, the data you've done here, can be extended, to other areas of the coast, or how would you approach, trying to figure out how this as an indicator can be used in other parts of the coast?
There are two ways. One is like there's a lot of folks working on really great models that show the spatial distribution of the whales and where they are likely to be seen. We can help validate those in real time and say, yeah, whales are here, and there's an action that needs to be taken. And second, we're working on a new proposal funded by OPC, where we will be comparing data collected on the Farallones with data streams collected in other locations to try to understand what are the similarities and differences, so we can try to keep an eye and be ahead of where the whales are and where they're coming, so we can so the managers can make the appropriate decisions. Does that answer your question?
I believe it does. Thank you very much. Okay, I think we'll move on to Karen Forney next. Take it away, Karen.
Great, thank you. It's an honor to be here. Thank you all. I'm looking forward to the rest of the meeting. And what I wanted to talk about today is some humpback whale models, some spatial humpback whale models that we've been working on. I've been the lead on that project, but I have a whole bunch of names listed here on this slide of all the people that have contributed thoughts and input and data sets that really have been instrumental to this effort. So humpback whale distribution models have actually been around for quite some time. And in large part, we've been working on these since the late 90s and all throughout the 2000s based on NOAA ship surveys shown on the left here with the green transect lines conducted since 1991. We use generalized additive models, that's a statistical modeling method, and to get habitat variables such as sea surface temperature and water depth and other factors from an ocean circulation model. And on the right panel are two examples of a habitat model for kind of an average distribution of humpback whales in 2005 and 2008. These are heat maps, or often called heat maps, where the red values are the greatest densities of whales and the blues are absent or low densities. Elizabeth Becker, I have a bunch of papers cited at the top. Elizabeth Becker is my colleague, and she has been the lead on a lot of these modeling efforts. So why can't we just use that model? Well, those models are really designed, they're very coarse. They are designed to come up with annual estimates overall, so they aren't temporally resolved very well. But even if we do project them into, for instance, here, these 4 panels in July of different years, we can see that they're rather coarse. The scale is 10 by 10 kilometers, and that really isn't answering the questions very well surrounding whether the humpback whales are feeding on krill on the right. These panels on the right show from an aerial survey conducted in a krill feeding year where the whales are just near the shelf break, and on the bottom panel is a year where they were primarily feeding on anchovies. And we can see that the scale of those shifts is very small compared to the pixels and the modeling effort. So what we wanted to do is come up with a better resolved, finer scale model that actually relates to what the whales are doing on the shelf in the area where the fixed gear fisheries are. This is my one technical slide in terms of methods, just a quick overview. I won't go into all the details, but we use basically the same methods that we have developed and that have been peer reviewed and published before. I limited this survey data set to 2005 onward, in part to get the most current data and in part because some of the habitat variables only exist after 2002. I excluded all the offshore survey effort. Our original surveys go over 300 nautical miles offshore, and really what we wanted to do was resolve the patterns that are on the shelf and slope. So I'm limiting the data set to the areas where the fixed gear fisheries operate. Shown on the right, a slightly narrowed study area. And I'm predicting on a finer 3-kilometer scale. We have a variety of habitat predictor variables that are similar to what we had before: sea surface height, mixed layer depth, and bathymetry, and then a product that I hadn't used before that I wanted to bring in, a very fine scale 1-kilometer level sea surface temperature that actually gets interpolated when there are clouds. So we have a cloud-free product and we can get a daily 1-kilometer product at a very fine scale. The other thing we wanted to do with this, in addition to getting a finer scale, is evaluate whether these models could be extrapolated outside of the July through November survey period. We've usually limited our models to July through November, but obviously the fishery operates exactly opposite that. So we wanted to see whether we could get a model that would be valid year-round or give us reasonable results year-round. This is a summary of the results, and I won't go into too much detail here, but these plots basically show on a relative scale the effect of temperature. So this one on the left is the sea surface temperature, and we can see that the densities are greatest in about 14 degrees centigrade, and then they drop off as water's warm. That's consistent with what Jaime just also told us, that there were some differences with sea surface temperature. And then there are also relationships with sea surface height, mixed layer depth, and water depth, so bathymetric depth. We predicted the model every other day and then averaged over 14 days in monthly periods to look at how the model would perform. And I have here on the right now, this is an animation that is running through, I think it started actually at the wrong place in September 15. It's from 2012 to 2015. Biweekly periods showing movement of whales. The blues are where the whales are largely absent. The pinks are where whales are present and not totally very concentrated. And then when we get into the oranges and yellows, those are times and periods when the whales are rather concentrated in a particular area. And what I'm hoping you will see that we saw that we were really excited about is that we are getting a north-south migration. So right now the whales, that was just a winter period, the whales were absent. They come back in, and throughout the summer, they are hitting the foraging areas, many of the foraging areas. So those vary from year to year, though, and even within a season, there's some movement. Now, some of this is what we were hoping to see. Some of it is not quite perfect, and we still have some work to do. But the initial step was to try to validate these models using some independent data. And I'm going to give just 3 examples of that where we're seeing things that look good and things that aren't quite where we'd like them yet. So what I have on the left side here is an aerial survey. The gray lines are transect lines that we flew. The blue dots are locations of humpback whales. This is in Monterey Bay, and we can see that the whales were very concentrated on this particular date, 16 October 2013, in the northern part of Monterey Bay. There are a few whales elsewhere, but not in the same high numbers. And the model during this period, this is the biweekly prediction surface, shows a hotspot in yellow in that same green circled area. So it's matching what we observed quite well with lower densities in those pink shades elsewhere. In contrast, this is a survey that was done in support of the California ramp in June of 2018. And we saw whales that were distributed in shallower and shelf slope waters, more widely distributed. And the prediction for this time period has pinks and yellows more widely distributed. So it's not as concentrated in Monterey as it was, but overall relatively good concordance. Again, not perfect, but picking up the general pattern reasonably well. An example off Oregon, Washington, we have much more limited aerial survey data there, but this is from a leatherback survey conducted in September of 2011. And they had both those crisscross lines and then some fine scale east-west effort. The blue diamonds are the locations of humpback whales. And we can see that they're generally in the areas where we had these pink predictions, so dispersed predictions for humpback whales, although in my mind, I see a slight mismatch right off the Columbia River where the model says we should have seen a lot of whales, but we didn't on the aerial survey. Could just be that we missed them, or it could be that the model is misinterpreting something there. So the other way we can look at this, and I apologize in advance, this is a messy slide, but I'd like to walk you through this. What we can do is look by region and see how well it's capturing patterns through time. And so on the x-axis, we have time beginning in November of 2009 and moving forward. This goes through September of 2013 right now. And the colors, the different colored lines are for the different regions. So red is Washington, blue is Oregon, and then the green, purple, and oranges are different portions of California. And the main pattern I wanted to illustrate is that during this period, this pre-marine heat wave period, and before the entanglement spiked, we had this nice increase in the summer and a decrease in the winter, an increase in the summer, decrease in the winter. And the timing isn't quite perfect. It's the increases seem a little bit later than perhaps the whales arriving, especially in the later years, but we are getting a nice seasonal signal. The model is accurately capturing then what happened during the marine heat wave. If we look over here on the right, where the seasonal migration signal was disrupted. And indeed, we had whales that were off along the coast all throughout the winter in various regions, and that contributed to the spike in entanglements. And so the model is picking up this, I kind of call it mayhem over here, that the whales are doing all kinds of crazy things. And then after the ocean conditions restabilized, we see a hint of this seasonal migration pattern. But again, this is not a perfect pattern. We're still seeing some variation across regions that'll need some further work. So just to wrap up, I just want to end on sort of some thoughts on what this model can tell us and how it can be useful and how not. Those of you who know me know that this first quote at the top is one of my favorites. All models are wrong, but some are useful. That was by George Box in a paper in 1979. And I'd like to also add that they're useful for some things and not others. And so the main thing that we want to do is understand what can this model tell us, what can it not tell us. So I'll start with the not. Models will not tell us exactly where the whales are going to be at any given time. They might point us to areas where we might want to put some survey effort in or look more closely or get some other data sets. So point to hotspots. Or timing changes, but they're not going to be an exact representation of what whales are doing. They're just a guideline of what we expect based on what whales did in the past. But what the models can do, and which I think you'll hear more about in Module 5, is they can allow us to explore different scenarios, management scenarios, and whale scenarios and habitat scenarios to try to identify what factors are most important for reducing or contributing to entanglement risk and which mitigation measures would be the most effective. So it's really an exploratory tool. If it's capturing some critical elements of what whales are doing, then we can use that as a baseline to try to explore different potential management actions and scenarios. And indeed, these models now are have been provided to my collaborators, Jessica Redfern, Jamil Samuri, and Chris Free, for 3 different projects that are looking at various aspects of entanglement risk and socioeconomic cost. You know, we want to find measures that won't cost the fishery much, so find the most bang for our buck. And we'll hear more about that on next week on Module 5. Jessica led just a straight look at entanglement risk and how that could be affected by some different management measures. Jamil is looking at a trade-off analysis, and Chris is looking at integrating harmful algal blooms, crabs, and whales together with this model. And I'll end with my thoughts on the model. We need to continue validating. I think Jaime and I have talked about combining our data sets, and I think there's great benefit to be had by validating and improving the models as we learn more. But at this point, I think the model is capturing these fine scale and temporal patterns that we want in order to be able to explore potential management options.
Right.
Slide here. And I just want to end then and thank you and thank all the people that provided funding support and for that.
Yeah, thank you very much, Karen. I think there's a time for a quick question here, which I think had to do kind of building off of Jaime's presentation and this notion of early arrival, and was that occurring in other places along the coast? And I know you had the mayhem slide there, but boiling that down, I mean, does that appear, at least from the models that you've got there, to be a consistent thing seen in other places as well? So early arrival.
I think, in short, I think mostly yes. It's a little challenging to compare. I mean, the model does show that during that marine heat wave period, the whales remained in the area longer and arrived earlier in the spring. So in the fall and spring, we are seeing that, and it kind of manifested that there were whales there virtually all throughout the winter. What's challenging is that the numbers that I have are large regional scales, and the information that Jaime has is really the point at the Farallones. And so I think if we can combine Jaime's data set with other data sets, maybe from Monterey Bay and other resources, we may be able to answer that question more fully. But I think in general, yeah, there is concordance that we were seeing a disruption or a change in what was happening during those years.
Okay, thank you very much. All right, so next up, Brianna Abrams. Brianna.
And Brianna, I think you are on mute currently.
Apologies about that.
No worries. I think, oh, here it is. Okay, we can see the presentation in full screen now.
Okay, great. Well, good morning, everyone, and thank you so much for having me today. Today, I'm going to talk about a model for blue whales, very similar to the model that Karen just presented for humpbacks. This is a product called Whale Watch 2.0, and I'll talk a little bit about the history of its development. And first, I want to acknowledge all the co-authors that were involved in this work. It was a large team of people from several universities and NOAA, and this work wouldn't have been able to have been done without them. So the history of this product started with my colleague Elliot Hazen's Whale Watch 1.0, which intended to predict blue whale distributions off of the US West Coast using satellite data that predicted distributions at a monthly scale and at a 25-kilometer spatial resolution. And the goal with Whale Watch 2.0 was to capitalize on new ocean modeling data that produced information about the environment and about oceanography that happened on a daily temporal scale and a 10-kilometer resolution. And that's called the Regional Ocean Modeling System that Karen also mentioned and used in her models. And so the goal here, like I said, was to produce a much finer resolution model of blue whale space use. And so to do this, rather than using survey data, we used a large satellite tagging data set on 104 blue whales that were tagged over a period of about 10 years. And so this is a little animation of that tagging data. And so you can see that the tagging data extends well beyond the spatial domain that we are particularly interested in. So I'm just modeling their space use in this black box here. And so we related their movements and the habitats they are using to the regional data, environmental data from the Regional Ocean Modeling System. And so this, as I mentioned, produces a picture of the ocean on a daily basis at 10-kilometer resolution that is also three-dimensional. So it includes a number of subsurface layers that we found to be really important for predicting whale habitat. And then I'm not going to go into all of the detailed methodology here, but we used general additive mixed models like Karen mentioned, and also boosted regression trees, which is another statistical model to relate these habitat or environmental variables to the blue whale movements and space use, and ensembled different models together because we found that those performed better in terms of predicting where whales would be. And that produced the result of our final model. And so what we end up with here is rather than density, we're predicting the probability of presence or absence. And so what we have is a scale from 0 to 1, where 1 is the red color here and indicates a very high likelihood of occurrence, whereas the dark blue represents very low likelihood of occurrence. And because the satellite tag data, the satellite tags stay with the whales for much of the year, and we have whales moving around. The input data that we used was whales moving around throughout their annual cycle, their northward migrations and their southward migrations. We were able to produce this model that predicts blue whale occurrence on a daily basis throughout the entire year. And so then one of the incredibly important steps in all of this is the model validation. And so we did a lot of different types of model validation that I'll go into with a little bit more detail. So the first one is called cross-validation, where we withheld some of the data that we used to train the model and then tested the model to predict how well it actually tested on that data that we withheld. So we did that with our satellite tag data to see how that performed. But more importantly, we tested on a large independent data set, and that included the whale alert data that Jaime talked about. It also included the Southwest Fishery Science Center survey data, and it included a number of other opportunistic sightings. And so you can see here that the majority of the sightings that we have are in Southern California, because that is where we were really focusing our efforts with this model. But we do have data that we use to validate that goes all the way up into Washington. And that includes, like I said, the Southwest Fishery Science Center survey data. And that ended up being over 3,000 sightings of blue whales, which is actually the largest blue whale sightings data set to be compiled and published together. So then the actual statistical metrics that we use to assess our model, we use two different metrics. And one of them I'll just go into is called the area under the curve, which is AUC. With AUC, scores of greater than 0.5, AUCs range from 0 to 1, and scores of greater than 0.5 are considered better than random predictions, and a score of greater than 0.75 is considered good. We calculated AUC scores for all of our cross-validation data sets, and also against the independent observer data set, which is a lot harder to get a good performance when you're testing against completely independent data. And we received a AUC score of 0.95 for that independent observer data. So we were very happy about that. And so now we can also look at how the actual spatial predictions line up with other studies that have been done on the same population. And we found generally good agreement in terms of where we are seeing hotspots of blue whale activity. So around the Channel Islands, around the Gulf of the Farallones, as well as Cape Mendocino and Cape Blanco up in Oregon. And so in the center here, there was a published study using the same tagging data that just looked at, wasn't trying to predict where they would be, it wasn't trying to relate it to environmental data, but just saying, okay, where are the hotspots of blue whale activity based on the tag data? And so you can see that it goes pretty much up and down the coast, and that's where we saw our tag data occur. But again, similar hotspots. And then on the right is Elizabeth Becker's model that Karen made mention of for humpback. Karen talked about it in the context of humpbacks. This is for blue whales. And we also see kind of high aggregations hugging the coast in similar hotspots. So we can also look at how our model predicts the timing of occurrence. And Jaime talked about this a little bit too. And so this is specifically in Southern California, where we looked at, okay, well, what does our model say in terms of when we should start seeing whales arriving, blue whales arriving, at least in Southern California? And so this is the curve from 2009, where on the x-axis we have the day of the year, and on the y-axis we have what our habitat suitability value is, which tells us the probability of blue whales arriving. And we see that there's this kind of curve where starting in the spring, we start seeing increases in whale activity, and it kind of evens out over the summer when we have a period of residency, and then towards the mid-fall or late fall, we see it dropping off again. And so that's a very typical curve that we would expect under kind of normal conditions. In contrast, in 2015, during the year of the blob, we saw a really different pattern where blue whales arrived earlier, or the model predicted that blue whales would arrive earlier and stay later. And that, even though this is Southern California, that seems to very much align with what Jaime said about earlier arrival seems to be correlated with higher sea surface temperatures. So again, this is just what the model predicted, but then we can see, okay, well, what does all that independent sightings data say about the time, how the timings varied from year to year? So we looked at when was the first whale observed in this area, and when was the last whale observed? And we can see that there's really good agreement with the model predictions in terms of the timing in these very different years of different environmental conditions compared to when whales were actually sighted, which is encouraging. We also then compared what were the actual model predicted values at actual whale sightings events. And so what we found is that higher habitat in areas that have higher habitat suitability, so values of 0.75 and greater, we saw many more whales being sighted. And we also saw larger group sizes occurring in areas with high habitat suitability as well. So this tells us that we can start thinking about some of these values in terms of when we see really good habitat suitability, we're much more likely to see whales actually being there. And so this model has already been published in 2019, and we also have a website on NOAA's Coast Watch that produces daily predictions from this model that are in near real time. So there's about a 12-hour lag. So these are already operational and publicly available data in terms of these whale predictions. And I briefly want to give an example of how this model is already being used in a different context for ship strikes to blue whales. So we are developing a tool called WhaleSafe that is actually going to be launched in a few weeks. And this tool uses 3 sources of input for assessing what the risk of ship strikes is to these whales. So one source of input is that habitat suitability value. Another is whether whales were detected acoustically, and another is whether whales were detected based on observer data. And so all of these feed into a whale presence rating that's low, medium, high, or very high. And based on what that rating is, then that information will be communicated to the shipping industry and ask ships to slow down, which has been shown to reduce the mortality of from whale strikes. And so one thing to note is that the habitat suitability value, that's just a prediction. That's not based on actual observation. And so the habitat suitability value, when it gets greater than 0.75, it can never be used to trigger a high or very high whale presence rating. Only the actual observations can do that. But it can kind of help put people on alert and go up to the medium presence rating. And then if we get an acoustic detection or a sightings detection, then that will kick that alert up a notch. And
Brianna?
Yes.
Sorry, I need to kind of to bring this in. You got one more slide for us here?
Yeah, this is just an example of what the website looks like, where we have this whale presence rating. Anyone who's interested can toggle on and off these observations of whales, as well as the blue whale model. And this was just to show, this last slide is just to show that whale presence rating can only really reach up to medium with it. And there is going to be a webinar on this, and you can follow that link with the slides that are shared after this presentation. And I just wanted to quickly end, kind of similar to Karen, when are model predictions useful in this context? And this model is also being used in some of those risk assessments, like Jamil Simhori's risk assessment and trade-off analysis that's going to be presented again next week. But model predictions are useful in this context when other data sources are not available year-round. When survey data gets interrupted, like during a pandemic, we don't necessarily, there might be a break in the data, and so you might need a model to fill in the gaps. When it's used as one of several sources of information in decision-making, so that the whale safe is an example of that, where this is just one data stream that's going into that whale alert rating, and when forecasting is needed. And then finally, just like Karen said, these types of models always need ongoing validation. And so data like what Jaime talked about is incredibly valuable for that ongoing validation piece. And with that, here are some more resources. And I don't know if there's time for questions now, but I can also talk during the panel discussion.
Yeah, thank you, Brianna. Yeah, I think we're going to have to move on for now, but I'm sure we'll circle back around to some questions, particularly about some this, how it's been used and how it could be used for the entanglement issue. Okay, so Jared, you're up.
Sorry. All right. Hello, everyone. Thanks to the convening body for allowing me to present. I'm going to talk about some ecosystem science and some for monitoring and mitigating entanglement risk. And I'm not alone in this effort. There are probably 100 people behind me helping to move this along. It's a major effort to synthesize all these data sets. I largely live in the realm of processing and analyzing and looking at sea data, particularly long-term collections. And this is an example of our NOAA ecosystem assessment surveys that the Southwest and the Northwest Fishery Science Centers have been conducting for many decades, one of which is nearing about 40 years. And these are midwater trawl surveys that are designed to capture micronecton and midwater small pelagic fishes, krill, invertebrates, and squids and things. But it's a massive effort, and all this collections are processed at sea. And there's a real wealth of data here that can be used to inform what's going on and define the ecosystem state and current ocean climate conditions that might be forcing these processes that we're seeing along the California coast. We look at the entire picture. We look at biodiversity signals. We look at all the small pelagic fishes, squids. We have visual surveys for marine mammals and seabirds, and acoustics that track hotspots of krill swarms. And we've kind of put this all together to look at this whole system, to really see the entire ocean ecosystem state and see how it varies from year to year. So we're not sort of myopically looking at just krill or anchovy or just, say, blue whales or humpback whales. We're really taking this whole big picture approach. Just some of the really large scale variation that really drops out of these massive data sets is that we have mechanisms that involve oceanographic processes. For example, when we look at how biodiversity fluctuates over the scale of some 30 years, we know that there's a strong relationship between source water variability that's entering the California current from either the north or south, that's subarctic and subtropical water. And during these years of really strong subarctic influence, we get a lot of a big spike in groundfish populations recruiting along the West Coast. And then one of the other revealing things when we split out our diversity signal, when we look at the rest of the assemblage that's not rockfish and young of the year groundfish, we see this really magnificent change in the diversity, where this low diversity state of this typical cool upwelling period versus this sort of really high diversity state, low abundance, low fat in terms of like the overall organisms that are entering the system. And this really shoreward shift in the thermocline of the upwelling system. We can actually look at also individual species, again, back to 1983, but this is just an example of data sets. Now, this is just data. This is not models, right? So this is observations collected during May and June throughout the California coast. And we can really track when these anchovy populations are starting to surge. So you can see periods when they're just not present or very low densities. And then by tracking the young of the year anchovy, we started to see this really incredible sort of growth that's really sort of booming throughout the California, in a situation we probably have not seen in like 50, 60 years, that along with some really, really high whale populations. I could probably give a whole nother talk just on this, but this is all you're going to see about the krill predictive modeling work that I and colleagues have been doing. We have a number of predictive krill models that range from mechanistic models that are fully coupled ocean ecosystem models, ones that are Lagrangian particle tracking or individual-based models, and we also have correlative habitat models that are in the same domain as what Brianna and Karen showed, and they're utilizing sort of the same sort of oceanographic modeling system underneath. But we have really long time series of euphausid or krill populations that could be broken out by different regions. So here's an example in the middle where we're using this observation data set by region to perform evaluations and parameterize these models on the top. But we're also pulling in observations from our long-term hydroacoustic surveys that actually look at the really fine scale patterning of krill hotspots and their relationship with submarine canyons. And these also extend throughout the entire California current. And on the right, we're connecting these models so that we can understand the pulses and variability in the biodiversity of the entire ecosystem state of the pelagic realm. Many should be familiar with this study, but this was really an easy thing to, well, easy in the synthesis part, easy in sort of getting it through and communicating it, building it out. But this paper was published earlier this year, and thanks to these really wonderful, rich data sets, we're able to put together an ecosystem oceanographic perspective on what caused, or sort of the underlying aspects of the massive spike in whale entanglements. And it's a hypothesis that combines this long-term increase in whale populations, the aspects of the marine heat wave and how it drives compression and an ecosystem shift between different forage states. But, you know, the end of the line, I mean, all you really need to know, if you want to go read that paper, but the guiding principle is that habitat compression, which I'll get into in a moment, alters the forage distribution and community structure, essentially the ecosystem state, which also then alters whale distribution and aggregation intensity. So that's been our working hypothesis for the last 3 to 4 years. But the question I always ask myself when I'm giving advice to working groups or to the public is, are we likely to observe an ecosystem shift resulting in the redistribution, increased aggregation, and residence times of whales in coastal waters? And I think we're all after that question with our different lanes of models and observations. And just to drive it home, and I think it could be an exciting example to try and recreate with some of the model output, but one of the metrics we develop is looking at whether humpback whale abundance coming from sighting surveys and say, here the central coast, and here's the distribution of krill hotspots that they normally feed on the outer shelf break during cool productive years. So we can actually detect a shift in the abundance and the aggregation intensity from moving off the shelf and the outer slope to the intercoastal waters. And so we've done a lot of work on that. But to kind of pull it all together and how we communicate and provide advice on this, and at least in terms of this ocean and forage factor that we provide to the California RAMP program, is this has been strategically designed and summarized to inform that factor. And this is a calendar event that years back, Karen Forney and I and others kind of put our heads together to kind of lay out a schematic, because it's really important to think of things with the seasonal cycle, and you heard about the whale timing and everything, but this is from the ocean and forage perspective. So our process compiles all the ocean and forage data, and we do ecosystem status reports with the CCIA and other projects like the Cal Coffee reports. And we combine all that data and we provide an outlook on what the forage conditions and ocean state is throughout the California current. During the winter, we switch over to monitoring these ocean basin and climate conditions and regional indicators to determine what's going to be the spring and summer date when we're actually out there actively collecting lots of data. And so this schematic, I'll walk you through with a couple of examples and then sort of unveil a now living document that's attached to the Santora et al. 2020 paper. The first one I'd like to show you is really important, and this gets beyond just looking at like the PDO or the Southern Oscillation Index, these climate state indicators, but what we really need are these regional spatialized oceanographic ecosystem indicators. And so here's a really great example that needs to be used more. It's called the North Pacific High, and it's really important for predicting spring ocean forage conditions, specifically on the shelf too. And what it is we're tracking the atmospheric pressure cell out in the ocean here, and we can track it in winter and time. And depending on the area and the size and the extent of that pressure cell, we have a really beautiful relationship between the productivity of krill and rockfish and anchovy on the shelf during spring. So we can look at the winter to predict the spring. Now let's just jump into the habitat compression and why we need it. It's a process-based ecosystem indicator. It's a spatial time series, just like the NPH. So we're actually looking at the amount of space or habitat here, and it's designed to reflect the area of coastal upwelling habitat. It's monthly resolution composed of 8-day estimates. Why do we need this? Because it's ecologically significant for understanding regional ecosystem and distribution shifts and the aggregation of marine species. And specifically, positive upwelling can occur during warming events, and that can be very misleading. And if you look over here at the upwelling indices during the heat wave, they were all average. And if we just kind of jump ahead here and look at an example from 2015 during the heat wave, there was cool productive upwelling, but it was really compressed along the shore. So that got us thinking and communicating with our fishing partners that we need some other index of trying to describe that habitat aspect. So the California, this is an example from the Central California Habitat Compression Index. It's monthly here, and we can classify into low, medium, high, and it's tied to this ecosystem state of expanded upwelling habitat, high diversity of groundfish, increased krill, and just the opposite once we start to get into a compression state of high. But you'll see that we've been in, since the large marine heat wave started in 2014, there was a little bit of recovery in 2017, but by and large, we've been in an extended sort of warming state for the past, 8 years. And this is tied to our community state that's coming from all of our shipboard surveys that we're tracking. And this is just some examples of different species that you can put together to kind of look at the connections here with the compression.
All right, Jared, it's Dan here. You got time for one more slide here.
Okay, then I'll just say that we've expanded this to cover the entire West Coast. Now it's regional sort of boxes up and down the coast, and we've seasonally adjusted this thing, but we don't have time to get into that. The last thing I'll quickly say here is that we've built a website that lives on the California Current Integrated Ecosystem Assessment, and it's rich, full of information. And I welcome you all to come here and take a look and provide feedback. There's a beautiful whale entanglement dashboard button that'll get you into all the nitty gritty, and you can build your own report card and look at maps and see all this data that we've been collected that was described in our various papers and research. And there's clear standardized thresholds and classifications for each one of these indicators so that you can interpret them, whether we're in some sort of low, medium, high, or strong, average, or weak state, depending on the indicator. And there's another tool that will even take you deeper if you want to actually see all the different trawl data and contents, and invite you to go and look at that as well. So I'll just finish here on this slide, Dan, here, and with some recommendations that I'll just leave up here on sort of the importance of incorporating ecosystem science into sort of strategic management decisions. And we really need these process-based solutions that account for climate change and variability. And so the mechanisms that I've been working are trying to account for these things, because we are going to be in this period where we have increased frequency of heat waves and the consequences of long-term ocean warming and a growing whale population. And we all need to do better on communicating and anticipating when this ecosystem state again changes, and how to incorporate that into decision making. And there's a big list of partners here, and I'll leave that up, and so we can move on.